In this video, we're going to take a step back and talk about some basic transistor applications. So the first one that I've kind of been alluding to a lot is amplification. So we can use transistors as amplifiers, and we know we want to be in the forward active mode. And so we're actually going to come back and we're going to talk about this in the next video where we look at an example. And we're going to hit on this a lot harder in the next unit as well, where we're looking at our AC analysis of our BJTs. So we're going to come back to amplification later, but let's take sort of a quick look at some of the other things that our transistor can do that we're not going to take a look at later on. So one important use for transistors is using them as switches. So a transistor, if we operate it and we have it change in between cutoff and saturation, we can switch some type of load. So I've got a simple circuit shown down here. So this load could represent anything from a light to a motor, really any type of thing that we would want to be applying electrical power to. And so the way that this works is that by adjusting our input voltage on the base, we can either have current in our load or not have current. So as an example, let's say we have a zero. So let's say, for instance, we have a zero input for our input voltage. Well, that's not going to be enough to bias this base emitter junction, which means our transistor will be cut off. And that means we will have zero collector current, and essentially we've switched our load off. So now if we have something large enough, so maybe we have, again, we want to be in saturation, so maybe we have something large, so maybe we have a 5-volt supply here. So now we forward bias this junction, and we're not necessarily worried about it being linear. We just want to have the maximum amount of current at our output. So now we'll have some IC that's greater than 0, so we're powering our load. So one sort of note on this idea of using transistors as switches. So here, of course, I've shown a BJT. More commonly, we're going to use the second type of transistor that we'll get into a little later in the semester, which is called a MOSFET. We'll see why that is, but ultimately what it comes down to is it's more efficient. We mentioned it briefly, but we didn't talk about sort of the mechanisms, but our BJT is going to have a lot of leakage currents or relatively high leakage currents compared to the MOSFET. On a single transistor scale, that's not so bad, but if we start using, thousands, millions, and even billions of these things, that leakage current can really start to add up and start to be significant power loss. So switches is an important application of our transistors. Another sort of related application is digital logic. So I've got a simple digital logic circuit here, and so if you want, what you can do is pause the video and see if you can figure out what digital function this would be serving. So the way you could do that is consider different inputs. So we could say if we have a 0-volt input and if we have a 5-volt input for our VI, what does our output voltage, which is taken off the collector, look like? So again, if you want to pause the video and think about that, go ahead and do that. So it's the same basic idea here with the circuit we looked at for our switch. If we have 0 input voltage for this configuration, we're going to have 0 current. So if we have 0 current, then we're going to have 0 voltage drop across RC, and our V out would just be equal to our VCC up here at the top, which is 5 volts. So 0 would correspond to a 5-volt output. All right, and so if we change this and we said now we want to have our 5-volt input, well, now maybe this is high enough to drive that, certainly to turn our device on. Let's say it's high enough to put it into saturation. So what we're going to see then is that, of course, we have some IC which is going to be greater than 0. The exact value is going to depend on our resistor, RB, as well as our BJT specifications. And of course, with a current IC, we're going to have some voltage drop across our resistor RC, which means our V out is going to be not necessarily 0, but we can see it's going to be pretty small, definitely less than 5. And so that's a whole separate topic of how do we determine what's small enough to be a logic 0 and a logic 1. But for the time being, let's just say that drops down close enough to 0. And so of course we can see the function that this is serving is this is acting as an inverter. So we can make a simple inverter with just one transistor and a couple of resistors. Again, just like with our switches, typically we're going to use the MOSFET transistor because they're more efficient, and we'll see why that is when we get into MOSFETs later in the semester. One other digital logic circuit to consider is, what if we sort of take that inverter and we put sort of a second inverter and we connect the two collectors together and we call that our output. And so we can sort of do a similar thing. We can make a truth table like we did for the previous one, but now we have two inputs. So for instance, we could say V1, V2, and we're looking for what comes out with our V out. So we have, of course, 4 possible inputs, 0, 0, 0, 1, 1, 0, and 1, 1. So if both V1 and V2 are 0, neither transistor is on. We have no current in RC, which means that our output voltage is going to be approximately 5. Now, if either transistor turns on, we are going to have current in here. So we're going to have, if we just have one of them on, so that applies to these two middle cases, we're going to have a smaller current than if we have both of them on. However, in both cases, we're going to say we have current, therefore we have a voltage drop across RC, so our V out is going to be less than 5 volts. And again, we're kind of glossing over some details, but let's say it's small enough we can count it as a logic 0, so we get something that looks like that. And again, I realize now that I've used sort of logic 1s here, but we could represent that as logic 1, or we could say instead of 1, these are 5 volts. So you'll kind of see either representation. And so sort of observing that, we can recognize that this circuit is providing a NOR function, so a not or. One other thing that I want to mention about our sort of transistor circuits here, we notice in this case we have 2 transistors in the circuit. So oftentimes with other components we have R1, R2, R3, similar thing for inductors or capacitors. And so it's no different for transistors. So usually we're going to want to label these so we can tell which one is which when we're referring to it or when we're doing calculations. And so the letter that we use for our transistors is typically going to be Q. The reason that we don't use T is because T is oftentimes used to refer to transformers, and the Q comes from some of the early packaging of our transistors, which if you look at it sort of from an aerial view, it sort of looks like a little Q because there was a little notch on a circular or cylindrical casing. So that's where that comes from. So again, it's just important to label those if we have multiple transistors in one circuit. One other thing I'll note is, again, we're not going to go into more detail with this digital logic, but if it's something that you're really interested in, you can look at chapter 16 and chapter 17 in the textbook, and that goes through the digital logic using transistors. And if I recall correctly, it talks about using MOSFETs for digital logic, but also using something called bi-CMOS, which is sort of a combination of bipolar and MOSFET transistors. So again, we're not going to get into that, but if it's something that is really interesting to you, I would encourage you to take a look.